Welcome back, Marauders. In this review video, we're going to be looking at the vapor pressure of water. So water evaporates, as you know. It can be a liquid at room temperature, but some of it will also evaporate and turn to a gas. And since it turns to a gas, it will have pressure. So all gases have pressure, including water vapor. Frequently, it's a kind of a common laboratory procedure to collect gases over water. So you might have a setup kind of like this, where a chemical reaction is taking place and gas bubbles through some water and then is collected above the water. Well, when you collect gas like this, you're collecting not just the gas created by your experiment, but also some water vapor, because some of the water in this container is evaporating. So when you finish your experiment, you've collected the gas, it contains water vapor and the gas that you were intending to collect. And so when this happens, you are looking at the total pressure inside this container. You're not just looking at the gas you're interested in, but it also includes the pressure of water. So you need to make sure that you subtract out the vapor pressure of water so that you're looking at and using only the partial pressure of your gas and not the total pressure, which includes both the gas you're intending to collect and the water vapor that's there as well. So the vapor pressure of water will vary with temperature. As temperature goes up, the vapor pressure of the water will increase because more water is evaporating. And when there's more water molecules in the container, then the pressure will be higher. So you don't need to measure the vapor pressure of water, but you'd look it up in a table. So this is a table of vapor pressures, and you can find different temperatures, and you can find what the vapor pressure of water is. And you would just look that up for the current conditions, and then you'd be able to subtract that out. So here's a typical question. Nitrogen gas was collected over water. So maybe an experimental setup, something like this, where nitrogen was being produced in a reaction, collected over water. And at the end of the experiment, we were at 30 degrees. We had 750 millimeters of mercury as the total pressure, and we had 0.35 liters of the gas collected. And so we want to know how many moles of nitrogen are in the container. So you might think that we're just going to use PV is equal to nRT. That's correct. So we'd take PV is equal to nRT, solve for N. So you get PV over RT. And so we plug in the values from the problem. We've got the pressure, the volume, the gas constant, and the temperature, and you get the number of moles of nitrogen. However, when we measured the pressure here, 750 millimeters of mercury, that was the total pressure. So pressure total was equal to 750 millimeters of mercury. And so that's not just the pressure of the nitrogen that we're interested in, it's also the pressure of the water vapor. So what I want to do is subtract out the pressure of the water vapor and then use PV is equal to RT again. So this is not correct, it's not accurate, because in the calculation we were doing the pressure of not just the nitrogen, but of all gases. So we're at 30 degrees, so we find 30 degrees here, and we find the vapor pressure of water at that temperature is 31.8. So the pressure of the H2O is 31.8. And so we can subtract and get the pressure of the nitrogen. And so the pressure of the nitrogen in this case is 718.2 millimeters of mercury. So everything else in our original calculation was correct. We just need to take out the 750 and plug in the 718, the pressure of just the nitrogen. So it'll look like this. The number of moles is equal to the pressure of just the nitrogen, 718.2, times the volume, that's still the same, 0.35 liters. The gas constant still the same, 62.36. And then the temperature, 303 Kelvin. So we calculate that, and we get N equals 0.0133 moles of nitrogen. So this is the more accurate calculation to find just the number of moles of nitrogen. This was the number of moles of gas total, but remember this included the water and the nitrogen gas. And so if we're only interested in the amount of nitrogen in the container and not the water vapor, then we need to first subtract out the partial pressure of the water vapor and then use PV is equal to RT with the partial pressure of just the gas that we're interested in. So you can see a small difference in this problem Because the temperature was relatively low, there was relatively little vapor pressure of water. As you increase the temperature, it's going to become a lot more significant. So if you have a higher temperature and you look up the vapor pressure of water, it's going to be contributing to more of that total pressure. So your answer will be further off when you forget to subtract out the partial pressure of the water as your temperature gets higher.